Okay, so good afternoon, everybody. It's an honor for me to introduce the 2026 speaker of the Henry Painter Lecture. So, before I introduce the speaker, I would like to say a couple of words of the lecture. So, Henry Painter was a devoted member of our faculty. He invented the bond graphs, a formalism to describe dynamic system across energy domains that inspired many researchers, right, and transformed the field of dynamic systems. So for this lecture today, I'm honored to introduce Richard Murray. He's a professor of controlled dynamical systems and bioengineering at Caltech. So Richard started his career with fundamental contributions in the field of robotics. His textbook on robotic manipulation is cited more than 11,000 times. He opened the field of cooperative control and control over dynamical systems, networked dynamical systems. And he has done that through many applications, including autonomous systems and synthetic biology. And today is presenting as autonomy. Thank you.
Fantastic. Thanks for that gracious introduction, Domitilla, and thank you to the department for inviting me to give the Painter lecture. I never met Hank Painter, of course, knew bond graphs as all of us did, but I think really systems engineering is something that we've all been inspired by in thinking about how to design complex systems, and as Domitilla said, that's really what I've spent my time doing in various ways. So today I'm going to talk about one particular type of kind of complex system that we'd like to think about controlling, and that's autonomous systems, one class of them. And I'll mainly, as you might imagine, kind of talk around this idea of self-driving cars as an example of autonomous system that needs to be pretty safe, right? And so I don't know how it is here in Boston, right? If you go to San Francisco, you see these things all over the place with nobody in them, or they're driving around, and we should be saying, as engineers, right? Are we comfortable with that, right? Are we okay with these things driving around? I put the Nutonomy up. There's actually the one I normally use. Nutonomy happens to be a company that spun out of MIT, no longer called Nutonomy, but nonetheless, has a heritage here. But it is the normal one that I use. As we kind of look at this particular autonomous system and think about it, we can ask, how do we make sure these systems are safe, and how safe do they need to be, right? And so one thing we can start looking at is just saying, okay, well, how safe do they need to be? That's a societal question, right? How much are we willing to tolerate? It's not going to be perfectly safe, right? People are going to get killed by autonomous cars. I'm sorry, that's going to happen, right? I mean, that's just the way things work. We want them probably to be at least as safe as humans, right? Should they be safer? That's a societal question. Can they be safer, right? Sort of what we do. So I want to talk a little bit about that and give you some ideas about that. So let's start maybe by just looking at cars and autonomy and say, well, how safe are they now? And so in the United States, you get about 7 deaths per billion miles driven. So that's a measure of safety. And that's pretty safe, right? Most of us don't drive a billion miles, right? Anything close to that. And so we can say that's pretty safe. Nonetheless, that's about 35,000 deaths per year in the United States, right, due to cars. And so you could imagine saying, suppose we could make self-driving cars as safe as human-driven cars. Would that be good enough, right? So now you have to start asking some questions. So you might say, well, let's suppose I had 1% penetration of self-driving cars. I can tell you in San Francisco, it is more than 1% already. Just look around, you will see, right, sort of out of 100 cars, 5 of them are probably self-driving, right? So it's already above that. If you think about electric cars, right, they have probably, gone past that already, right? So if it was 1%, what would that mean? I mean, 350 deaths per year, that would mean every day, right? There is a death someplace in the United States where a self-driving car killed somebody, all right? So MIT graduate student gets killed walking across the street, right? Caltech faculty member gets killed, right? Driving, run into by a self-driving car. I would argue that's probably not good enough, right? Probably the industry would not survive if every day there was a headline saying self-driving cars are killing people, right? They're killing people all over the place. So we probably need to be safer than that, right? So how safe, right? So then we can say, okay, well, what's the safest mode of transportation? That might be another thing to compare to. And so one thing you can look at is the airline industry. We can argue about whether this is the right metric or not, but there it's about 100 times safer, right? So 0.07 deaths per billion miles flown, right? Should we do hours or miles, right? Good question, I did miles. But nonetheless, it's 100 times safer. And of course, If we were 100 times safer than humans, that would almost certainly be good enough, right? At 1% penetration, that's 3 deaths, right? Every 3 months somebody dies, right? Even if we were only 10 times safer, right? Then every week and a half or so somebody dies. And so you say, geez, somebody just got killed. But you say, yeah, but in that time, look how many, right, humans got killed by, right, sort of humans driving around. This is so much safer. So probably, right, how safe is safe enough? In principle, right, sort of 0.07, I would argue a factor of 10 is probably enough. To make those things safe, we have air traffic controllers. We have, sort of hugely complicated requirements on how you, sort of certify software and other things. I'll talk a little bit about that. And it's expensive, right? About $1 million a seat, right, would be one way to think about it. So for $1 million per seat, right, we could get 0.07 deaths, right? Are we willing to pay $4 million for a 4-person car? Don't know, right? So someplace in there is your range, right? So I think that's sort of worth thinking about. And so that's kind of the framing for this talk, right? Sort of how do we tell how safe they are? How safe should they be? How safe is safe enough? All right, so, and one of the things, is to ask, can we get there? Right? Is that even possible? Another thing to ask is, can we take the lessons that we learned, right, for making these systems safe and apply them back, right? And so I'm going to do a little bit of both of those things, right? What are the challenges? What can we take from the aviation industry where we have a huge record of safety developed over, right, 100 years and do that? Okay, so what I'll talk about is kind of the motivation. So I'll talk a little bit more about autonomous vehicles, talk about some tools that we might use. And so I'll talk about some formal tools that we might use, something called linear temporal logic, and then talk about some of the work that we've been doing at Caltech in the area of operational test and evaluation, and then give you a little bit of some open problems spread throughout, not necessarily just at the end. Okay, so if we dive into one of these autonomous systems, and again, think self-driving cars as a model for that, we might say, okay, well, what's inside, right? And so a relatively typical architecture for a self-driving car might look something like this. And so we'd say, look, we're going to break this problem up. We're going to do an architecture for the control of this. You've got a physical system sort of down there at the bottom. It's interacting with the external environment, right? The road, the physical part of the external environment, all of the other cars that are around there, all of those things. And then we have a number of layers, right, of kind of both sensing and information processing and control. So sort of sensor and information processing on the left, control on the right. So we might have a lower layer, stay in your lane, control the speed, come to a stop at the right spot. We'll have some intermediate level that kind of red above there, right? What's the other things around me? What's the trajectory that I should use, right, in order to do that? And then some supervisory layer, right? Do I stop and wait for the other car? Think of it as a discrete decision-making layer. Is it my turn to go, right? Sort of things like that. So that would be a pretty standard architecture. And on the control side, you're making decisions. On the sensing side, you're trying to understand the situation, right, and reason about it. And in the middle, you maybe have some online model of both what the world looks like. If I turn, will other people slow down or not, right? That's one of the questions you have to ask because it's a reactive system, right? So we have to think about all of those things. And so it's a pretty complicated system. It's a system that has, these days, lots of processors inside, lots of things going on, lots of optimization happening in various places, trajectory optimization, graph search, other things, lots of increasingly machine learning going on, especially on the kind of sensory side, right? Sort of classification, prediction, other sorts of things going on. And there are lots of places where these sorts of architectures come up. So I'm using self-driving cars as the example, but this is also what an aircraft control system looks like. To some extent, this is what a factory automation system looks like. Smart buildings, the power grid, they have these layers, right? These layers do different things at different timescales, and we separate the problem out because as engineers, when we separate that problem out, right, we can sort of define it. And so I think, there are questions at the design level about how do we define these different layers, what are the interfaces, how do we scale to many devices where we've got lots of cars. Lots of really interesting things to ask about. But I think all of these are things that we can sort of think about as that's the underlying design framework. One thing that's changing is that now many of the things that we would have thought about on the right-hand side, so controls people, right, we're going to do a PID controller, we're going to do model predictive or receding horizon control, right, we're going to do things like that, are now being taken over by machine learning methods, right? Why don't we just learn the feedback controller, right, off of data-driven things, et cetera? And that's a perfectly valid thing. It does not change the question that I want to ask, right? How safe do they need to be? How do we make them safe? How do we know that they're safe enough, right? And so I think all of that is sort of changing quickly, but fundamentally the question for me is not how do we design these, right? That's a great question, lots of people working on it, but how do we verify and validate systems with this level of complexity and say they are safe enough to put out there? You're the VP of engineering for self-driving car company X, right? And somebody says, please sign a line and say this software build is good to go, right, in the city of Cambridge, Massachusetts, right? Because I believe it's safe enough, right? What do you do, right, as that VP of engineering, right? What are you looking at? How do you do that? So that's kind of what I want to talk about. Okay, so I think one thing that's interesting about this space is that there's lots of stuff going on. And so we can think about, in a very simplified way, right, the problem we might be trying to solve is that you have a continuous dynamical system, the car, it's got forces, right, you can use a bond graph to model all of those things. It's got discrete decision making, right, so I've written that here on the left as something where I have a guarded command language. I have a guard. If that guard's true, I apply a rule that changes the state, right? You come to a stop. When you see that it's your turn to go, you say go. I go into go mode, right? Things like that. And then we're solving the problem maybe by a combination of things. We might be using optimization. That optimization might be encoded as a sort of reinforcement learning problem, right? But someplace in there, there's a cost function, right, or a reward function that you're trying to optimize, however you do that. And then you also have discrete variables, right? You know, if the other person got to the sign before me and they're on the right of me, then I have to wait until they go before I go, right? So these kind of discrete sort of rules. And each of these, right, you know, sort of pieces has to be broken down in that architecture. And so as you go through looking at what the dynamics are and what the lower level controllers are and the higher level, et cetera, you have different representations of these problems, right? So you might have physics down at the very bottom, right? You might write differential equations and other things, and I might think about what's the operating envelope energy efficiency at the design stage. As we move up, we might do things where we say, great, this is an inner loop problem, I got disturbance rejection and other things, so the controls engineers will sort of recognize, right, sort of the terms there. Then I got to optimize some trajectory, so now I have some cost function, again, depending on how you want to do that. And at the highest level, I probably have a finite state machine, right, that keeps track of what state I'm in, what state I think the rest of the world is in, right, and then I make transitions between those discrete states. And then I've written down a specification that's in temporal logic, and I'll say a little bit more about that. Okay, so I'm going to talk mainly today about things that are going on sort of at this top layer and the next layer down. So this coupling of discrete and continuous decision making, and I'll give a little bit more sort of background on those pieces. Okay, so this is the class of systems I want to look at. I'm going to argue, think self-driving cars as an example, but the power grid, aerospace systems, manufacturing systems might have different levels of safety. In the end, right, you've got a system that looks like this. All right, so now, you know, what do we mean by safety, right? That's another question. And there are kind of two classes of safety that I want to talk about. And, you know, these are the words that are used in the autonomous car industry. Functional safety versus what I'll call operational safety. So functional safety is really the thing that we're very used to, especially in the aerospace industry, which is we want to make sure that if there is a failure, the system continues to operate properly, right? If the engine fails, right, at 30,000 feet, you shouldn't all of a sudden come plummeting down, right? You want a redundant thing up there, right? And so we have lots of redundancy and other things. And so typically the way that we might do that, for example, is we might use something where we have a fault tree, right? And we would say, okay, I have some subsystem that needs to have a failure rate of 10 to the minus 8th. And so I say, how could that system fail? Well, any one of 3 different things could happen, right? And if I want to have no more than 10 to the 8th, then the typical thing you do is say, great, I'm just going to take a factor of 10 more safe, right? So the components, right, need to be at 10 to the minus 9 failure rate, right? Some of those things may be things where 3 different things would have to fail in order for that component to fail, right? So for example, the electrical power system of an aircraft is typically powered by 3 or more different things: the left engine, the right engine, and the APU that's in the back of the aircraft, the auxiliary power unit. And all 3 of them would have to go out, right, in order for, right, me not to have any electrical power. And under some assumption of independence, right, that there's not a single mode of failure that would cause all of them to go down, I can say, great, if each of them are good for 1,000 hours, right, mean time between failure, then roughly speaking, right, I get 10 to the minus 3rd for each, and I just multiply these together to get 10 to the minus 9th, right? So that's kind of the simple fault tree analysis people do. Obviously, you can do more sophisticated things. You can put in all the correction factors for correlated things, et cetera. So this is what we would do in aerospace, and this is why I can fly back to Washington, D.C., where I'm living right now tonight, and be pretty sure I'm going to get there, right? 0.07 per billion miles flown. It's not very many billion miles, right? You know, the likelihood that I don't get there safely, very small. The likelihood's good that I'll get there safely. Likelihood that I die is very small. All right, sorry. Got to get the logic the right way. Definitely don't start putting the, you know. All right. Operational safety is different, right? Because I could have nothing fail, right? And I could still, right, have an accident. For example, here's, you know, picture sped up, obviously, from downtown San Francisco. There's a lot going on, right? There are people, there are cars, right? You know, they're going, there are lights, there are all of these other things. Everything can be operating exactly correctly, and I could still have an accident, right? Because if somebody jumps in front of me from behind a car, right, and there's just not physically time for me to apply the brakes and stop before I hit them, I'm going to hit them, right? And you can argue that there was a failure, the person shouldn't have jumped in front of me, but from me, the point of view of the system, right, that's not a failure I control, right? That's simply somebody came in front of me, I'm going to hit them. So we call that operational safety, right? So how do we do operational safety? And sometimes you'll hear this called SOTIF, safety of the intended function, right? So How do I make sure that the system operates properly, right, when there was not a failure, right? Maybe a failure in assumptions, right, but not a failure of a physical failure. And so this idea of operational safety is important. And of course, we need to test both of these, right? Because you could have a flat tire in your self-driving car. You don't want that to cause an accident, right? Or you could have a situation where somebody was making a left turn and they blocked my view of the bicycle, right? So I didn't see them and I started going through the intersection and then I didn't have time to stop over the bicycle. Okay, that's a SOTA failure, right? That's a failure, an operational failure, right? And I want to minimize those too, right? I don't want to hit the bicycle when I could see them, right? I want to sort of know that. Well, why didn't you see the bicycle coming way earlier, right? And sort of predicted it might be there and, go a little bit more cautiously, right? And so that, would be the type of thing you'd like to do. Okay, so how do we do all of those things? So there are a lot of tools that we can apply, and I'll kind of go through some of these. And, for each of these, I'll say a little bit about what the idea is, and then, sort of what some of the open questions are. So one that's sort of the thing that, we're all, most familiar with maybe in traditional engineering is we'll just do something analytical, right? We'll write down a differential equation, we'll make a Lyapunov function, we'll say it's stable by virtue of analyzing this thing, right? So it's an analytical thing, it's correct by design. I'm gonna design my controller so that my, Lyapunov function, right, sort of has the right sign, and it's correct by analysis. I've got equations, I analyze those equations, right? And often we use this at the early stage. I at least want to make sure I've got enough actuation authority, I've got the actuators and the sensors in the right places, right? I can do simple models, I can tell you that all of that works. And so this is good for early system architecture, but it requires usually pretty simplified models that we know are wrong. Usually requires pretty simplifying assumptions, right, other things. But it's a great way to start. And there's lots of things that you can do, and many people in the field are doing things. And so, when we look at pictures that are, sort of standard control system diagrams, or things where we're looking at different types of level sets, barrier functions, regions of attraction, right, and reasoning about those. These are all analytical methods for doing this. In the world of linear temporal logic, at that higher level of abstraction, you might look at composition, and I say, look, I've got one set of specifications, I've got another. When I compose them, right, does that composition satisfy my system level specifications, right? So if I put these two components together, it'll work. So these are all analytical methods, and we write down equations for those things. That's certainly one way to do it. Another thing that you might do is say, that's great. It's very analytical. I'm going to write equations down. I'm going to reason over these formally. A different thing I can do is essentially just run simulations, right? Monte Carlo simulations. Build a pretty good model of my system. And in that model of my system, I'm just going to simulate as many things as I can. I might use software in the loop, actually run the real software that's going to run against a simulated model. I might do hardware in the loop, run the software on the hardware, right, and try and simulate the inputs to the hardware. So I'm really testing as much as I can. But it's still a simulation, right? The environment, the world around me is being simulated. It has the advantage that it's offline. It's parallelizable. I can run all those simulations, right? Especially if it's software in the loop, it's just software. I can run 1,000 of these things on a GPU cluster someplace. I can do a lot. But of course, it's still model-based, right? So I have a sim to real gap, right? Okay, great. I'm safe in simulation, but that's not the actual system. So how do I deal with that? It could still be computationally intensive depending on how high fidelity things are. And so we can think about, ways to get past that. Can we do multi-resolution simulations, simulate simple things when it's simple things work well enough? Can I sample near the failure boundaries? I don't want to uniformly sample, and I'll say a little bit more about this. So the picture here is one that came from Dana Fremont, who's now at UC Santa Cruz, and Sanjit Sesha, where they were looking at parameterizing a bunch of left-hand turns with pedestrians, right? And they were just looking over some parameterized space and running a bunch of different simulations, right? So, you're going to make a left-hand turn. There's a pedestrian coming through the cross-section, right? Where are they? Where do they start? Where do you see them? What's your speed? All those things. They're all parameters. Sample over that space, run 1 million simulations. Say the failure rate was 1 in 1 million, all right? Not good enough, right? So you probably need to run 1 billion simulations, right? Okay, it was 1 in 1 billion. We're getting closer, right? 7 in 1 billion was sort of our numbers. Okay, so that's one thing you can do. The other thing you can do, of course, is do real-world testing, right? Now, the disadvantage here, you're using a model. Let's go out and test in the real world, right? And so this is a view in San Francisco. I have an apartment there. This is actually looking out my apartment window. And these things that you see there, the white cars, the little things, those are Waymos. This is, I was giving a talk at Berkeley. I said, I should take a picture. This is the picture on my window. 1, 2, 3, 4 Waymos sitting there, all right? There are pedestrians crossing, they're waiting. This is just, real time. This is what's going on, right? There's another Waymo that just came in, 5 Waymos, right, in this scene. This was not me waiting there for 2 hours, and it was like me going, I should going to give a talk this afternoon, I should do the real one. Go outside, picture, oh my God, right? I got all of these Waymos going through. None of these have drivers in them, right? They're all self-driving, right, doing this. And you see them, they're waiting until the pedestrians cross, right? And then they see that there's an opening, right? Okay, good, now I can go, right? I mean, that's a decision-making system. That's a, path planning system. That's a lower level loop, right? All of that's running all the time, right? Great, so we can go out and test all of those things. And then we just drive lots of miles, right? Good. So how many miles do you have to drive in order to get a 95% confidence that you have 7 deaths every billion miles? Probably more than a billion miles, right? In fact, Rand did the analysis on this. For 95% confidence, you have to have 8 billion miles, all right? Great, 8 billion miles. I just did a new software build. Need to make sure it works. Go drive 8 billion miles. I've got a 1,000-car test fleet. No problem. Each of them drives 1 million miles. Oh, and I need the answer in a week. It's not going to happen, right? I mean, we're doing software builds all the time, right? So this is great, but it's just not going to give you the type of data that you need, right? You're just never going to test your way out of this problem by doing real driving. All right, so maybe, say, okay, what else can I do? Well, another thing that you might do, and you're going to do this, is you might say, well, I could do regression testing, right? I could save the logs from those miles, right? And then the next time the software build comes out, rather than me driving the miles, I'll just go rerun the logs through the software, right? So I take the log, right? I record it. I then inject it through some harness into my autonomy stack, right? So I feed all the sensors, right, with whatever's going on. I feed that in, and then I say, well, here's what you did before, here's what you did now, and I can compare them. And what you want is that most of the time you do exactly the same thing. But of course, you changed the software. That was the point, right? You sort of updated the software. And so you certainly want to fix the things that went wrong, right? When I almost ran into somebody or ran into somebody, I don't want to run into somebody. But the problem is you also change other things, right? Because all of a sudden now you slow down a little bit more, right? And when you slow down a little bit more, in real life, the world reacts to you differently, right? In not real life, the car behind you runs into you. Because the car behind you is a driving log and it didn't know you slowed down, right? I mean, it's just doing what it did, right? So now you have to throw that one out, right? Because you say, well, that's not realistic, right? Because, really what would have happened is, right, that obviously they would have seen me slow down, right? And therefore, so I'm going to throw that one out. Okay, is that real? I mean, maybe, right? Maybe will you slow down too much and they couldn't have stopped, right? So how do you know, right? So how do you decide? So this also has problems, right? How do you handle the divergence problem, right? The log starts to diverge from what your simulation does, right? And how do you decide that's okay or not okay? That's another problem. And finally, there are probably more than this, but the last thing that you might consider doing, or that I'm going to say that you might do, is you might say, well, what I should really do is I should go out to a driving range. So this is M City in Michigan. Turn sideways, the M should be sort of vertical. But M City's, right, a spot out, sort of near Ann Arbor, where they've got a, driving range set up, and they can say, oh, great, let's get a car coming through at the right speed, and they're going to put something in front of you. And then the good news is I can rerun that, right? I can say, okay, you had a failure there, do the software build, go rerun it, do the same thing, right? You think you're going to get 1 million miles, right, on M City in any period of time? No, right? You're going to get, right, maybe you're going to get 1,000 miles, right, of that, right? Which 1,000 miles should you run, right? Which scenarios? How do you know, right? So you're going to have limited testing time. You're going to have very simplified scenarios. It's very expensive. Okay, so I think all of these are sort of interesting. And, I think one question is you have to say, how do we combine them, right? And so you can say, for example, I can run, roughly speaking, this is an infinite thing. It's analytic, right? You get an infinite number of simulations by doing one analysis, right? Because it analyzes everything. I can do lots of these. Maybe I can do 1 billion miles of simulation and prove my simulation's good. Maybe I can get thousands to, right, sort of maybe millions of real world test stops, right? Total miles, right? Across my entire fleet. Regression tests, right? You can pick the number, right? But, probably less, right? Because a lot of them diverge. So it's something in the middle of this, right? And then the structured stuff, right? Maybe you get 1,000 miles of structured testing. And so I think it's an interesting question, right? So again, independent of how you think about design, et cetera, how do you combine these techniques? And what can we do to improve these techniques? And so I've written down, for each of these, what are things that you might do to improve all of these? And so I think just, for those of you who are interested in this space, I think this is a great spot to do research, right? And it's, you can just say, oh, AI is going to go answer this question, right? Maybe, all right? Where's it getting its data and how accurate is that, right? I think we want more than that. We're going to certainly do that as well, right? But, I think we want more than that. And so I think it's a great thing to think about where that is. Yeah.
So, but I will why is that only true that because actually combine and simulation with real time, right? Understand why.
Yeah, so for example, I would tell you, if I'm testing the logic of intersections at pretty simple things, right? Then probably simulation's fine, right? Because it's a kinematic simulation. What matters is did I get there first or did it get there first? It's pretty simple, right? I would believe the logic could be tested at that level. If you're saying it's raining and it's a little bit foggy and you were going a little bit too fast and the light turned, right? Is that simulation the right simulation? Not a kinematic simulation anymore.
That is not.
It could. And so I think that's one of the interesting questions, right? How do we, couple these, right? And so, exactly, right, to that question, how do we combine them all? And not just combine them by saying I ran these open loop, right, but also saying how does this inform that one, right? And I'll say a little bit more about that. One thing I think is interesting is, if you look at these, there's this one down here at the bottom that says defining coverage, defining coverage, defining coverage, right? Because in the end, you're trying to say, I've covered all the scenarios you're going to get. Good. How many driving scenarios are there? A lot. Every single one's unique. So what do I mean? Do I want to say, for example, well, I've seen you take a left turn before, therefore all left turns are safe. I just need to do one of those, right? You'd probably argue that the left turn on this intersection is different than that intersection. Oh, by the way, there's construction stuff there, and so that's a little bit different thing. And there's different pedestrians. Oh, there's a bike lane there. Okay, those are all different things, right? Do you want to cover all of those? Maybe you want to say, you know what? If you're going to drive in Cambridge, Massachusetts, I would like your autonomous car with a test driver to have driven every road at least once. I think it's not an unreasonable thing. Great. What time of day? Right? In the middle of the afternoon? In the morning? When it was raining? When it was icy? Oh, all of those. Well, now all of a sudden, right, how many road segments are there in, Cambridge? How many different temperature conditions, right, it's crazy, right? But you might also see, look, this intersection at this time of day is busy. And that intersection at that time of day is busy in the same way that these other 20 intersections at that time of day are busy. So let me drive them all once, but drive this one at a bunch of different times of day, right? And then I get credit for everything else. That sounds like a great idea. What's the math that says that's a great idea? I think it's an interesting question, right? So I think this coverage, right? Do you want to see every action? I'd like to see you turn left, turn right. Do you want to see every road? Do you want to see a response to every environmental condition? All of those are different things. So I think this coverage question is really interesting, and I'm not going to talk about it all. This is like if you say, I'm going to finish my sabbatical, go back, that might be the one I think about, right? Sort of how do we define coverage, and how do we actually do coverage, right? All of those things, right? Okay, so I'm going to talk about, some easier ones than that. I'll say a little bit about two of these. One is just what should we simulate, a little bit to your question, right? How do I use simple simulations when they're more complicated ones? A little different in your question, but some. And then the other is what should I test, right? If I give you 1,000 miles of testing, which test should you run and why, right? And how might you do that? Okay, so those are the two things I'm going to talk about, with a little bit more technical background. Okay, so let's start, with just this one about simulations and what we might do. And so, no question we're going to use simulation like crazy, right? It's offline parallelizable, right? It's got some cons. It's based on the model. It might be computationally intensive, just copied from the other chart. But maybe we can do things like multi-resolution simulations, use simple simulations when we can. So we might think about, in some abstract operational space, I might have multiple different models, right? Here, V1, V2, V3, V4. These means in this operational space, model number 1 is accurate. In this operational space, model number 4 is accurate. And maybe model number 4 is a lot simpler. It's 1,000 times faster than model 1. So if I'm testing in the operational space where V4 is, right, dry roads, very good visibility, not very many cars around, right, I should use that simple model because it's enough. But if I'm testing on icy roads with limited, things and very crowded, maybe I need V1, very expensive, right? So how do I know where are those boundaries? This looks good, right? I got nice circles and ovals, et cetera, but how do I even know where that is, right? And so when do I use them? How do I figure out where I use them? And so one thing you can say is, well, give me all the models, and I'll just sample and ask, if I say V1 is my high fidelity model I'm going to take as my truth model, right? I could say, okay, give me the regions in operational space, right, where the two seem to overlap, right? And so, the simple kinematic model works as long as you're going slow enough and the roads are dry and other things, and I have a simulation that I can do with wet roads, right, and all of these other things. Great, that's the way to do it. And so, one easy and obvious thing you want to do is to say, okay, well, how do I figure out this region? So if you imagine, that's V4 and this is V1 or something like that, right? What you probably don't want to do is uniformly sample, right? Because that's not very, and again, remember, this is a huge dimensional space, right? Not two, right? What you might want to do is say, well, let me try and sample around the edges, right? Because that's what I care about, is where's the boundary, right? If I say, this model is, V4 is really good here, I don't need to do a bunch of samples right around this, right? Because I know it's really good. If it's really good, right, then it's probably really good nearby under some continuity assumption. Same thing, if it's really bad over here, probably bad nearby too. So how do I, sample near that edge? So one of the things we thought about, and I think, relatively obvious way to kind of approach is say, how do we know how to sample near the boundary when we don't know where the boundary is? And so one way you can think about that is to use some sort of Gaussian process model, right? And sort of say, okay, I'll take samples and then I'll use those samples. If it was really safe over here, I'll assume it's pretty safe, right, on some distribution, et cetera, right? And if it was really unsafe over here, I'll assume that. And then I'll look for places where when I say, how safe is it here, right, off of this Gaussian process model, right, I can say, oh, that one I'm not so sure, right? And so you can imagine doing this in a way in which, and here's all of the sort of math where we sort of say, what do we mean by close enough, right? Keep track of the probability that I have the right sign, where I have a metric function that says, am I close enough? And that metric function is some function, sort of giving me that the model is negative or positive means that it's sort of the error is, sort of greater than some threshold, for example. Okay, and then you can sort of say, great, now how do I turn this into a sequential sampling algorithm, right? So I start by sampling the 100 points randomly chosen, right? And then from those 100 points, I put together some sort of Gaussian process representation. Say, great, where should I sample next? Where I think the probability is, right, that it's, sort of at the edge. So you sort of see, as you might imagine, how that works, right? And so here, just on some simple functions, right? Some things where I say, great, so how quickly, right, can I reduce the error signal, right, between the two different models, right? And so if you do intelligent sampling, you can do that quickly. So I think, I'm not going to say a lot more about it. You can read the paper if you're interested. It's the one that's up there. But I think it's an interesting question. And, part of it is, as usual, what's the metric that you use to decide they're close enough and why? So there's still, right, either some engineering judgment or some optimization that you need to do. But I think that we need to do more, and this is just a start, at thinking about which models do I use where and why and how do I define those, right? And there's another little piece that I think is also important, is sort of hidden in here, but the thing you want to do all the time when you're doing simulation-based testing is you always want to sample near the boundaries of failure of one model to match the other, but also failure of the system, right? So somebody at one of the autonomous car companies, the VP for engineering, CTO actually said something that was very interesting. He said, okay, we're running all of these simulations, like half of them should fail, right? Because, if most of them are not failing, you're wasting your compute, right? You want to be right on that boundary, and if you're right on that boundary, half of your simulations should fail. You couldn't stop in time, right? And then you can go back and say, but that's okay, right? Because it was not possible to stop in time, right? So how do we find that boundary when we don't know where it is? These types of techniques work there too. So I think that's an interesting question. Okay, so one thing, just a little thing is, I think there are interesting ways to think about what model we use, why do we use that model, how do we have a hierarchy of models, how do we choose which model we use, and how do we embed that in this overall kind of operational test evaluation. All right, so another thing that I want to talk about is how do we define the tests that we want to run. And so remember, I want to do this at these higher levels of decision making, maybe coupled to the dynamics. And so I need to introduce a little bit of mathematics in terms of what we're doing to kind of explain how that goes. And so we use temporal logic as a way to mathematically define these discrete decision-making systems. So let me just tell you a little about mathematical logic, the temporal logic. You won't be an expert, but hopefully you'll be able to read some of the slides. And so the idea in temporal logic is you care about sequences of actions, and you care about the ordering of sequences of actions. And there are three operators that we use, eventually, always, and next. And so we think of this as something where there are steps every time an event occurs, which doesn't have to be uniform, but you could think of it that way for now. Time step occurs. But every time an event occurs, then I can ask something about it. And so we say that something's eventually true if it may or may not be true right now, but at some point in the future, it becomes true. And then after that, don't care. It might become true, it might become false, but at some point I know it becomes true. Something is always true, right, if it is true now and it is true forever. And something is next true, right, if it is true at the next event time. And we can imagine that, sort of pictorially, right, something, just the invention always, right? So not some appropriate atomic proposition A is not true, not true, not true, at some point it's A, and then I don't care, right? And, A could be, could become true any place, right? If it's always true, it needs to be that atomic proposition. The statement that can be evaluated true or false needs to be always true. And then, of course, more interestingly, we can kind of combine things, right? So for example, we can start writing logical formulas. Like P implies eventually Q, right? If the light turns red, eventually I stop, right? P, let's say always eventually P, the third one down, right? So you got to read these symbols, always eventually P. What does always eventually P mean? It means that something happens, and then it happens again, and it happens again. For example, always eventually check your rearview mirror, right? Not check it once, and then you're done, but check it again, and check it again, and check it again, right? And after you checked it, check it again, right? At some point, right? So I'm just saying, if you stop checking it, you should check it again. Right? That's what that's saying. Eventually, always P is like a stability condition. It's eventually true that P will be true always, right? So eventually you're going to be, sort of within 1 meter of the center of the road, and you're going to stay there forever, right? If you wrote that down. All right, so you can combine these operators in interesting ways. We can also turn these into things that are not exactly just binary. We can start things and not kind of arbitrary time. We can put continuous functions in here, right? So some voltage, if it happened to be a power system, has to be always less than V max. We can write things like that. We can put time bounds on it, so you can use metric temporal logic or signal temporal logic. So these are variants of this. So something needs to be true but time t1 and t2, between time t1 and t2, not forever, ever, but in that time, right? Or maybe we say, if the light turns red, then within the next 5 seconds you should stop, right? And so you can say that something has to happen eventually in a certain time frame. Okay, so this is this idea of temporal logic, and so we can start writing down specifications in this language. So for example, if I have a stoplight, this is a European stoplight, right? I might say that, for example, the finite state machine, right, that describes this is, it's red, and then you see the red and the yellow come on, right? And then the green comes on, and then at some point the yellow comes on, and the red comes on, right? And you say, what are the properties that this stoplight satisfies? If I was designing this, right, you might say, well, I'd always eventually like the light to turn green, right? Because I want it to turn green, and then you can do anything once, but I want it to turn green again. That's a good property. I'd always like to be the case that if it's green, it's not red at the next step, right? So you can't just have it go green then red, right? That wouldn't be good, right? So you can write, all the rest of these. This last one's more complicated. It goes yellow before, right? If it's always the case that if it's red, then it'll eventually turn green, and it will not be green until it turns yellow. The U I didn't explain to you, but that's sort of the. So I can write these things down right in this way. And you can put time in here. I want it to happen at a certain amount of time. All right, so the point of all of this is I can take something that is that discrete decision-making layer and write it down in a mathematically formal way. And once I have it in that formal way, I can reason about it in that formal way. And in particular, I can use a lot of the different tools. I'll just briefly introduce a couple of these. So one is model checking. So the idea on model checking is I have some finite state machine that we call the system. I'm at this discrete layer. I have some specification on the right-hand side. And then model checkers essentially take the opposite of the specification, right? And then they ask, can you find a sequence of actions that violates the specification? So a model checker finds those things. And so when it does that, it checks over all possible executions, right? So for all possible combinations of cars coming up, et cetera, right? Can I find any combination where you turned in front of a car when you didn't have the right of way? And it will either say the specification is satisfied, that is, I could find no counterexamples, right, for the negation of the property, right? No satisfying traces for the negation, that is, no counterexamples. Or no, the property is not true. And the great part is it gives you a counterexample. And the reason that's great is because all engineers believe they designed their system correctly, right? And then you say, yeah, but what about this? And they go, oh yeah, that's right. I forgot. Yeah, okay, I got to go back and design it, right? So it comes up with a counterexample. So model checkers are wonderful tools. I don't think, computer scientists use them all the time. We use them for things like schedulers and other things, right? To make sure that scheduling works the right way. And so they're quite good. And they will check against all possible execution traces, right? So if you have a system that's got lots of things going on at once, you say, well, what if that car gets there before that car? What if it's the other way, et cetera? It will check over all of those. And they can handle sort of billions of discrete states, right? So they can get pretty big, and they can do a pretty good job. And so they're very nice for kind of, proving things, right? And we want to sort of say, this is an existing technology, right? These tools exist, and we want to make use of them. So for example, one of the ways that we can make use of it is to say, okay, well, how would we do that in system design, right? So one is that I've got a system model. I've got some assumptions about what the environment's going to do. I have a set of requirements, right? So I've done a design. I've got a system model. I've got a bunch of assumptions about what the rest of the world could do. I've got my specifications. And a model checker will basically say, take the system environment model, combine it with the formal specifications, and ask, is that always satisfied? It either is, and I'm basically saying, yes, you have a certificate, or it's not, and I give you a counterexample. But the other thing you can do, right, is you can kind of turn this around a little bit. And I should say, these tools exist. There's a whole bunch of them here, right, that will do model checking for you. You can go out and sort of look these up. But the other thing you can do is you can kind of turn around and you can do it to do synthesis. That is, I give you the system and the spec, and I say design the finite state machine that satisfies it. It's a little bit like LQR for control people, right? I give you the cost function, I give you the system, I say synthesize, right, feedback controller that minimizes that cost function. I give you the specification, that's the cost function. I give you the system description, x dot equals ax plus bu, right? And then I say synthesize for me here. This is done on that finite state machine side. And these tools exist also, but they're not very much used. And I'll tell you 2 reasons why they're not used in a second. Okay, so they're not yet adopted, but we want to kind of take advantage of these. Okay, so I want to talk about the synthesis problem because I think it's interesting for people to know a little bit about. I won't say a whole lot about it, but you can think of this as a feedback control design problem, right? We've got a process. It's a finite state machine process. We have an environment, that E up there, that's what the rest of the system is doing. Who's coming up to the intersection when, and when are they allowed to come, and when are they allowed to go? And we need to design a controller. Do I stop? Do I go? Do I turn left? Do I turn right? I mean, all of those are discrete decisions. And we want to design a controller such that some specification is true, right? And the specification I've written here, I won't read through. It was actually for an electric power system that we were doing jointly with United Technologies, Aerospace Systems, maybe now, 8 years ago or something like that. But we want to synthesize the logic for turning on and off, right? The power supply for an for an aircraft, right? What if the engine goes out? How do you make sure that the right things get power? Okay, so it's an interesting way to think about these things. And the reason that nobody does this is that the complexity is doubly exponentially big in the size of the specification. So you give me 5 specifications, it takes 2 to the 2 to the 5th, that's 2 to the 1,000th. You give me that's pretty far already. You give me 10 specifications, it's 2 to the 2 to the 1,000th. Okay, more than the number of atoms in the universe, we're done, right? We're not gonna do anything. So it's just intractable. Great, wonderful, can't actually solve it, not good. But it turns out that there are subclasses of problems that are pretty descriptive that are much better. And so there's this one subclass of problems called GR1 problems, and this is now 20 years old, that Pitterman, Pinelli, and Sarr sort of solved. And they made a couple of assumptions. They assumed that the environment makes a decision about what it's going to do. The process or the controller gets to look at that decision and make a decision, and the environment doesn't get to change that decision. And then they both implement their decision. And you say, well, that's not reasonable. Why does the sort of controller get this kind of extra benefit? And one way you can think about it is, well, if I'm going fast enough, that's probably good. As soon as I start to see the car going through, I can assume it's going to go through for the next 10 milliseconds. Yeah, okay, that's maybe okay. So it's an approximation, right? But it's maybe not unreasonable. Avoids race conditions. But essentially that allows you to sort of break this loop, right, into some sequential process and allows you to reason about it a little bit differently. And so in particular, for that class of systems with this assumption about the execution model, there are a class of specifications in which we can say, if I have some specification for what the initial conditions are, I know I start within a certain speed or something like that. I have some assumptions about what the environment can do. I know that the cars aren't going to ram into me on purpose, for example. I have some progress conditions. I know the cars will not stop in front of me forever. Eventually they'll move. Then I want to make sure that I always stay safe. I never run into any cars, and eventually I get to my goal. Right? So this class of specification is called a GR1 specification. So there's an environment assumption and a system guarantee. And it turns out for this class of problem, it becomes cubically complex in the number of states. That's like saying it's a convex program. Actually, it's like saying it's a linear program. Oh, that's different. We can solve big problems, right? So now these get to be a little bit more interesting. So now you got to ask, is this general enough of a class of specifications? I'm going to argue too that it is. All right, so just one example of this. It would be, think about the following very simple problem just to illustrate how this works, right? And this is out of some work by Pinelli. So I've got 2 agents, a runner and a blocker. The runner can be in a discrete state here, is where it starts. It can either move up here or it can down here. And then from one of these 2 states, it can move to the goal. So G is the goal. The blocker sits in the middle. The blocker can either move up, back to the middle, or down. That's what it can do. And the game is, I want to find a strategy by which the runner can get to the goal without the blocker being in the same place at the same time. Now, if you think about this, you say, okay, well, this is impossible, right? Clearly what the blocker does is it just stays in the middle, and then as soon as you move, I move on top of you. But I'm going to make the assumption, right? I'm going to make a couple. I'm going to say the blocker cannot stay in the middle forever. It has to move, right? Now that changes things. It can't stay in the middle forever. As soon as it moves up, what do? I move down, right? As soon as it moves down, I move up. And then, of course, it tries to get back to me. Before it does that, I move. Right? So you can imagine that that's the strategy. So how would we synthesize that strategy? So what we do is we enumerate all of the possible states of the system. Here it's a small number. So if each of these boxes has the runner and blocker in one of the possible configurations, the top one is the starting state. The bottom one is the goal state, right? And the bottom, what I want is I'm over here. Actually, strictly speaking, there's 3 goal states. I could be here. I don't care where the blocker is, right? But I'll just simplify it. And then we, sort of label the transitions, right? We sort of say, well, how can I get from here? The runner can choose a move, right? That's the red arrows. The blocker can choose a move. That's the red arrows. The runner can choose a move. That's the blue arrows. This is the system graph. This is all the possible things that can happen. And I say, great, I want to get down to the winning condition at the bottom, and I want to avoid the 2 losing conditions where it's on top of me. So think of the following algorithm, right? Start with the winning condition and ask yourself the question, what are the set of states such that if the blocker takes a move, the runner can find a move that brings me to that winning set, because then I win. And if you think about that for a little bit, you'll figure out that that's this set of states. Because of course, it's sort of dumb in this case, right? The runner moves down, I move over, right? The runner moves up, I move over. Right? Now you say, great, this is also a winning set. I win from this condition. What are the set of states for which if the runner takes a move, the blocker takes a move, the runner can find a move that brings me back to that set? And so if you do that, you get this set of states. Now I have my initial state. So now I know there's a strategy, right? Because if the blocker moves me to the left, I need to take the arrow that brings me back in the winning set. And there's only one action there, and so I choose that action. And then once I'm there, doesn't matter, I'm going to get back to the winning set. And of course, it's a finite graph, and so this expands, and if it expands and includes the initial condition, we're done. We win. And so from this, you can now extract a strategy. Right? And so I can essentially extract out, right, what is the strategy that is corresponding to that. So I can synthesize a strategy. Okay, so how does this apply to anything that we care about, right? This is for design. Well, we can use the same strategy to design tests, right? I said we've got this complicated situation, right? Can we do something where we can ask the question, right, how do I design a test? So this is from the DARPA Grand Challenge. This is in 2007. This was a test that DARPA had set up where we're in an autonomous vehicle, there's nobody in this thing, right? It comes up, came to the intersection, right? We wait until it's our turn to go. We now go, right? And so, for this, they designed the test. They said, this is a good test. We're going to bring stuff up. And then we come up to the next intersection. And at this intersection, as you'll see, they've sort of set it up. We're sort of wobbling around a little bit. Inner loop's not doing such a good job. PID didn't solve the problem. This one we come up, and now there's a car. I have to wait for that car to go, right? And we're step farthest back because that's the rules. Now that car's gone, so I can come up to the intersection. I come up to the intersection and stop. This car hasn't gone yet, so I have to wait till it goes. So they came up with this test, right? And they said, this is a good test. If you can solve this test, we'll let you go on. So I think you can think about, okay, well, how did they come up with that, and is that a good test? And I mentioned this sort of coverage problem and other things, right? So what if we could do something where we could synthesize the tests, right? I tell you, here's what I want to test. You synthesize where should the environment cars be, right? So that, right, I test the specification. I'd like to make sure I can do an unprotected left-hand turn. I'd like to make sure I can go through an intersection. Synthesize a test for me. Now we can use synthesis. But we're not synthesizing the controller. We're synthesizing the environment, okay? And part of the reason people don't like to synthesize a controller is you get something that you can't recognize as code, right? It's like the output, right, from LLM coding way back before it got good, right? I don't know what the hell this thing means, right? But I may not care for the environment, right? I'm not going to read that code, right? I just need to run that code, and I need to know it works. Okay, so that's kind of the idea. Okay, so you basically do the same winning set construction. And the way that this sort of plays out, I'll skip some of the details. You're welcome to, I'm happy to give you the reference to this. It's up there. Is that we're going to think about this in the context of a specific problem. So here's something where we're trying to get a legged robot to move around, and it's got to make decisions and other things. And the way that we structure this is we say, okay, I'm only going to focus on this top level. And at this top level, I have some rules that I want to be in place. So I have a finite transition system. And I'm going to write all of that down as these kind of finite transition system, right, sort of situations. And then what I'm going to do is I'm going to take that and create a graph of what the environment and the system can do. This is the big graph. I've got what the system can do. I've got what the environment can do. You can take the product of these two things in the right way. Say, here's all the things that the overall system and environment can do. And then I'm going to ask the question, okay, so now, right, suppose that I start someplace. I want to get someplace, right? I want to make it through the intersection, but I want my test to show me something. And that test to show me something means I want to make sure that I go through some intermediate node. That's where my test condition is satisfied. Right? So now I'd like to synthesize a strategy that does that. So the first thing that we have to do is we have to say, well, I want to make sure that I eliminate the possibility of the car doing the wrong thing. You come up to the intersection, I want to see you turn left as an unprotected left-hand turn, right? And you turn right. Well, I didn't do my test. So how do I stop that? I put a car or a cone on the right-hand side so you can't turn right, right? So I do something where I block one of the paths. So the only thing you can do is do the thing I want you to do. And so, but I don't want you to do it in a way where there's only one action you can take at any point, right? Because then that's boring, right? If the only thing you can do is satisfy my test, right? I want to give you as much freedom as possible to screw up, but I still want to see my test satisfied. So that was the problem that we tried to do. And we could turn that into a linear program, right? You could actually solve that as find what, so here's the long linear program, but it's what's the minimal set of edges that I have to block so that you have the maximum number of paths, right, all of which go through I and eventually lead to G, right? And then I can synthesize off of that a strategy for what the environment has to do using those synthesis tools. So that's the idea. Okay, so let me just sort of show you that in pictures. So here's one where we've got a robot that's going to start here. The goal of this robot is to get to the target. But I would like to see this robot go through 2 regions, both of them, right? This one has rocks in it and this one has snow in it. I don't want to just see you go to the target, right? I want to see you go through rocks and I want to see you go through snow, right? Because that's the test I want to do. So one thing you can imagine, you say, great, first thing I'll do is I'll block off some region, right? So that in that blocked off region, right, now you have to at least go through I1 or I2, right? You can't just, before I could have gone like this, right, if I didn't put that blocked off bold part. But now if I put that blocked off bold part, right, you could go through 1 or 2. If you go to I1 first, so you go over here, now I don't want you to go up this way. So I need to put something that blocks that off. That forces you now to come back around the other way. Okay? But I also want to do this in a way in which I've got another vehicle in there that's doing that, right? So we're going to synthesize a strategy for the environment that implements this specification. Okay, so this is what that looks like. So here's one robot is trying to get to the target up there. It goes through I2. This guy is my environment vehicle. It's reactive, right? It knows where it's going. It says, I think you might go to the target. I better get up to where I can block you. Oh, I see you're going to the target. I'm going to block you. Ready? Okay, well, in that case, I got to turn around and go the other way. Now, right at this instant, it can go back through that, middle part, right? So I see it going back, I'm not going to let you go that way, right? So I'm going to block that off as well. This is completely synthesized, right? We just gave it the specification, said you come up with what that middle guy should do, right, in order to make sure they go through I1 and I2, right? And then we synthesize the strategy. So that's kind of the idea. So now we can say, what set of 1,000 tests do you want to run? Well, give me 1,000 test specifications. What do you want to see? And we'll synthesize an environmental strategy to go run on the test track. And you can start telling me things like, I want to see you do an unprotected left-hand turn with 2 pedestrians and a bicycle coming through in this rate, right? And I want to make sure that, right, you sort of do all of those things. Okay, so I'll stop there. I've told you a little bit about how to make sure autonomous systems are safe enough, or at least some ideas about how to do that. Brute force isn't going to do it, right? I gave you this statistic, right? 8.8 billion miles per release, not going to do that. Simple models aren't going to do it because then you're just testing your model. So we need to do stuff that's sort of in the middle of that. We need to use a combination of these methods, and I've shown you a couple of those methods. I talked a little bit about this one. I talked a little bit about this one. I didn't talk about this one. This is another theory one, right? But I think we need to figure out how to combine all these things, and I think there's a lot to do. And the one thing is that, still missing a little bit is that the community needs to figure these things out. And the aerospace community, there's agreement amongst all of the airplane companies about how it is that we test these things. Self-driving car companies, not so much. They're not talking to each other right now. I think that's something we need to do. There's likely to be iterations between industry and government control. Right? In our current administration, right, we're sort of seeing let them go, right? All of those things. If you're in California, they don't say let them go, right? They sort of say, hey, if you do something bad, we're going to take away your license, right? So that we have to work through. This happened in the aircraft industry too, right? People started dying, and then they put the FAA, and they say, you can't just go fly something. You got to prove to me that you can do it, right? But it does feel a little bit like the Wild West right now. So go out to San Francisco and ask yourself, do I feel confident stepping in front of a self-driving car? And I hope the answer is no. Okay, so I will stop there. Thank you very much, and happy to take questions.
Thank you very much for the inspiring talk. Are there any questions?
Thanks, Richard, for a great talk. So I wanted to bring the common statement that circuit designers have, which is the freedom from choice, right? And so where is the role of architecture here in limiting all these options?
Yeah, so maybe just say a little about, what we do often in electric circuit architecture and other things, we do, some sort of platform-based design, and that allows me to separate the problems, and now I've made a choice, right? And so now I'm not leaving everything free, right? I'm structuring it. I think it's a good question, right? So one of the things I didn't talk about is I imposed a certain structure on the controller architecture that also allows me to impose a certain structure on the test architecture, right? Because I just want to test that top block and I know what the specs for that top block are and I do the next one, right? So now I'm constraining the problem and I'm not letting you do anything. I worry about the end-to-end, right? If I do end-to-end machine learning, right? You take pixels on the inside and I give you, currents on the outside for the motors, et cetera, then I'm giving the LLM, or whatever, the machine learning technique, complete freedom to do anything, and there's no structure to it, right? And so in the same way that we want freedom from choice in design because it helps guide design, helps it be more efficient and satisfies things, I think for testing, we want an underlying structure so that I can test as well, right? And so I would argue that if I was a self-driving car company, I don't want to give you freedom to do anything. I want to say, no, I'm sorry. You have to have an estimation block that estimates, right, sort of where you are, where other people are, because that's built into my test strategy. That's the way I get that. So that's one answer to that.
Any other questions? John.
Thank you, Richard. For the self-driving example, I think a big part of the picture currently looking at the Waymo deployment is the role of the human operators. So I think a lot of people don't realize that Waymo have remote human kind of helpers. No, they're not teleoperating the robot, and they say they don't control them. They give the robot advice. How do you factor in like a remote human helper into this sort of framework?
Yeah, so I think there'd be a couple of things I would say, John. So, one would be to say I should fit that into my overall safety model, right? Because if you want, right, one of the things I can do is I can say call for help, right? And so if I get to a situation I haven't seen and I say, okay, one of the things you talk about is the exposure analysis, right? How often does this situation happen, and what's the likelihood I'm going to satisfy it if that situation happens? And one thing you might say is that's pretty common. And I don't think I have a high enough safety rate. So if I look at the number of exposures and my kind of failure rate on that in a particular scenario, it's too high. So I'm going to increase that by calling in teleops, right? So I'm going to say, hey, I'm going to stop and wait until you tell me what to do. So then you can factor that in, right? When I have teleops. And then you can start saying, okay, do I have a teleoperator sitting on top of every car? Do I have one sitting on top of every 10 cars? One sitting on top of every 100 cars? If it's one on top of every 100 cars, what's the time delay in both me telling that operator to do that and them getting enough situational awareness, right? So that would be one way of thinking about that is how do you just factor that in, right? And you can do that with the person in the car as well, right? So how good are they at giving you extra safety?
Thanks. Well, can I follow up? If you can use your influence at the Academy in Washington, they're incredibly secretive about this whole aspect, So they recently said, I think that at any one moment there are 70 remote operators roughly split between the Philippines and Arizona, and it's order of 40 to 45 cars in action per one operator, but it took, I think, testifying for Congress to get that out of them. And so do you have how do you open up the conversation about what's really happening with remote teleoperation?
Yeah, so I mean, okay, well, I'll just say it more generally, right? I mean, I think it's always this problem that the companies, we had a project now ended, but where we tried to get the companies to say, what research problems should we be solving, right? And nobody would talk to anybody in front of anybody else, right? So nobody wants to admit what they're doing, right? Nobody wants to say we're 1 per 50, right? Oh my God, they're doing 1 per 50, we're only doing 1 per 10. I've now got competitive knowledge, right? So I think that that's hard. And you can then impose on everybody that they have to satisfy something. You have to tell us how many operators, et cetera. In that particular case, it might not be bad, but if I impose some constraint, for example, I say everyone has to have 1-to-1 on top of it, right? Then I start limiting the innovation, right? Because now I can only test, I gotta have a whole bunch of people in the Philippines that are doing this. I can't test as many cars. So they can argue they can test 50 as many cars. So that balance, I think, is always there. One of the things that we see is this shift. You see in the aerospace industry where the aerospace industry just does everything on their own, however they want to do it, right? And then something bad happens, a bunch of people die, et cetera. And the government comes in, as they should, and says, you can't do that, right? We're going to impose a bunch of restrictions. But then those restrictions become onerous, right? And then all of a sudden the companies say, well, like Airbus is out competing us, right? Because we're having to satisfy. You see this, by the way, in drugs right now in China, right? Everybody's worried that China's moving faster on clinical trials, right? Because we have a set of, restrictions and they have a different set. So then, the government is the bottleneck, and so then you pass it back, right? You sort of say, okay, well, how do we do that, right? So for example, in the case of aerospace safety, we said, what we'll do is we'll allow the industry to check the standards that government is imposing by hiring the people who do that, and if they want to move faster, they can hire more people. Well, that's what the Boeing 737 did, right? And now you've got the problem that your testers work for the company, right? Or your safety people work for the company, right? And, do I flag this thing, right? Yes, right? But, well, I do that. So I think we'll see that go back and forth. Right? I completely agree with you. Right now, there is no transparency about what's going on. There's no, Waymo's been pretty good about at least saying, here's our statistics, right? Here, and they seem to me to be comparing apples to apples near as I can tell. If you look at human drivers, they say they're 4 to 5 times safer than human drivers. We can all ask, is that safe enough? And they say, and we're comparing, comparable things, right? We're not sort of saying human drivers in really complicated situations and ours on really simple situations. But I think there's still not enough transparency. So, I put this one here, right? I had a conversation with Emilio Frazzoli, used to be a faculty member here, about this. How do we get an industry, like, the SAE or the other people who come together and say, we need to figure this out, right? And right now, my sense is that the industry doesn't believe that government's going to do anything, and so they're not motivated to do something first, right? Maybe that'll change. We'll see.
Okay, so last question, and then we say goodbye.
Hello, and very nice talk. So I want to ask a question about the second point here in this slide. So a combination of different methods. Do you feel it's enough to just apply these methods in parallel, or we need a meta theory to synthesize or formally combine all the results, or something in between?
Absolutely think we need a theory to combine them, right? Some of that's just simple statistics, right? I have from this thing, this kind of, probability. I have from this thing, this probability, right? The coverage gets hard, right? So, I'm testing different things in different places. So how do I combine those? I think that's a little bit of it. I'm not sure I'd call it a meta theory. I'd probably just call it a theory, right? And to the point that Lindsay brought up a little bit earlier, right? I think you want to also say, how do I use one to trigger another, right? So how do I say, hey, I got a failure here, and that failure may not be accurate relative to the model, so I'm not going to go 10 different simulations and see. And then, oh, by the way, I'm not going to bring those statistics back into my model, right, and sort of use that. And I think, how do you do that? When do you do that? How much credit do you get for doing that? How do you get credit for saying, I've done a bunch of log tests in this type of a scenario, and therefore I don't need to do a physical test in that scenario, right? And again, that requires some theory to say, well, what's your probability, right? Your belief function, right? That the simulation test is close enough to the real test that I don't need to do it at a level of 1 in 10 to the 9, right? So, it's 1 in a billion, right? So the factor of 10 better than the 7 in a billion is 1 in a billion-ish, right? And so, I think that's the target. A lot of people who are doing distributions and other things are saying, oh yeah, we can estimate the tails. Okay, this is like a really, really, really far out tail, right? So it's really hard to get all of those failure cases, right? Because every accident is unique in its own way, right? Maybe rear end ones are the ones that are relatively simple. Somebody stops too quick and you run into them, right? Every other accident that occurs is because somebody did something and your kid was yelling at the time you were changing the radio and somebody got in front of you and you crashed in them, right? Okay, how do you find all of those things? So anyway, I do think that a theory is needed, right, to combine all of these. And I think it's more than just simple statistics, right? Because you want to look at the structure underneath those statistics to figure out how to combine them. Okay.
Okay, thank you very much. Before we thank Richard, we have a present for him from the department. Hopefully not.
So this looks safe, right? Yeah.
There's a bond graph over there.
Fantastic.
Thank you very much.
Thank you.
Thank you.